I know we still have some time, few minutes, but I wanted to write down this limit we will use today, later today, this one. So I had several questions about the squeeze theorem, how to prove the inequality that is required for the squeeze theorem. And the answer for that is that, well, it's not always easy. Well, you need to just make sure you understand whatever is in the level of our course. But one of the examples I love a lot is this sine x over x. When you try to evaluate this, you notice that this is 0 over 0. And, well, it's not a polynomial over polynomial so that you can factor cancel, yes? The tool which helps us to evaluate this limit is a squeeze theorem. And proving inequality that will help for this takes a little bit of time. I posted a video on our page. So if you check instructor section page, you go down, there is now a page called limits. You will find the videos there, you will find lecture notes there, and there's this specific video proving this thing using a squeeze theorem. Make sure to watch that. This is a very nice example of a squeeze theorem, and well, the inequality is not clear how to prove at the beginning, but this is something that we will get back to it later on, but I'm hoping that you now see it because we will use it for something. Any questions, any comments before I start? Okay, so that means that we can start this new topic, continuity. Remember that so far, when we have been working on limits, we specifically said that evaluating limits has nothing to do with the value of the function at that point. Indeed, we are not required to have a function which is defined at a to be able to find the limit. The only thing we need is f is defined around a, not at a. But we want to relate these two things, and the relation comes for the first time as part of continuity. So let me write down the official definition or mathematically precise definition here. So let f be defined at a and around a. So if it was only limit, you would see me writing f is defined around a. But now I want not only at a, but also around a. We say f is continuous at x equal to a if. So I know that you guys already have an experience working with the continuity, but today we are going to focus on what mathematically continuity means. Here, it means that, or in general, not only here. First of all, the limit as x approaches to a exists. Also, f is defined at a, so I can evaluate it at a. The third thing is that the limit and the value of the function are the same thing. Before, we didn't even need to have the right-hand side here. Now, we're saying that if it is defined, the limit is equal to the value, then we say f is continuous at a. And otherwise, this is the terminology, f is discontinuous at x equal. So when you're checking continuity, there are actually three things that you're checking. One, the limit exists. Two, the function is defined at that point. Three, they are equal. And that is basically the steps that you have to run whenever someone is asking you if the function is defined at a given point or not. So let's do an example here, which is a graph example. Check the continuity of f at x0, 2, 3, 4, and 5. What is f? So my function f this is 1, this is 1, 2, 3, and 8, 4. And then that. Point. And so this is 3, this is 4, and the value is really low. Okay. So we have this function, this is given, the graph is given. Now, I want you to go through these points. For each point, you want to say something. You may have a good feeling what is continuity, what is not. But I want you to take care of those points by checking these things. Does the limit exist? Does the function, or is the function defined at that point? Are these two values equal or not? Okay? 90 seconds for this? Yes? Go ahead. Focus on your writing. You're trying to see how you can follow the steps written on the board. Go ahead, please. 30 seconds left. Okay, let's start. Continue checking continuity at any point means do those three things. Limit of the function as x approaches to 0. Well, as x approaches to 0, from both sides, this function approaches to 1. So that's the first thing. The limit exists, it's equal to 1. The second thing is that what is f at 0? What is f at 0? Yes, please. Not defined. There is a hole there, meaning that there is no point above x equal to 0. So this is not defined. Well, then fail. The second question, second part failed. Then there's nothing to check further. So this is f is not continuous at x equals. At x equal to 2, we do the same things. Try to find limits of the function as x approaches to 2. What is limit of this function as x approaches to 2?
Minus.
What is it? Positive or negative infinity, yes? So that's the other way of saying does not exist. If I want to say more details of that, if I'm approaching to 2 from the left, it goes to the positive infinity. So negative upper one goes with the positive, lower one goes with the negative. Doesn't matter if both of them were plus infinity again, this does not exist. And then so f is not continuous at x equal to 2. So one of the conditions fails, you don't need to continue. Someone can ask, what is f at 2? F at 2 is not defined, even if it was defined. Even if I had a bullet there, f at 2 is 0, but the limit does not exist, so I cannot do further work there. For the limit as x approaches to 3, well, I heard that it does not exist, but the type of work I would like you to do for that does not exist is this, that, okay, when I'm looking at the graph, I notice that from the left, from the right, it is using different branches of the graph. And I can see that if I ignore the right-hand side, from the left when I'm approaching, the value of the limit is negative 1. Okay, it doesn't matter what is that number at the moment, but somewhere there, yes? From the right, it is, what value is that? It is positive 1, just 1, okay? The reason for the limit at x equal to 0 does not exist is this, that the left and right limits are not the same, so the limit of f as x approaches to 3. So you have to clearly write down what causes does not exist here. Here, the left and right exist, but they are not equal. Well, obviously, that means that f is not continuous at x equal to 3. There is an interesting case here that the right limit is equal to 1, and the value of the function at 3 is also 1. Even though the limit itself does not exist, but if I just consider right limit and the value of the function, this is called f is continuous at 3 from the right.
Does not exist like this.
Yes, so we have one-sided continuity. It will go exactly the same story. We just consider one side of limit. At 4, limit of f of x as x approaches to 4, it's a number somewhere there. Well, I already draw something for 2. It really doesn't matter what is that value at this point. What matters is that I see the values around 4, they're approaching to the same value as the value of the function. Okay, is that value 2? Sure, you can write it as 2. It's 10, right? 10. But what matters is that those are approaching to the same value of the function. Yeah? So it is continuous, so f is continuous at that point. How about at 5? Is function continuous at 5? Yes or no? How many yes? How many no's? Oh, okay. I'm interested to hear why no's at 5. Can anyone volunteer for no? Yes. So you're saying it's not continuous at 5. Yes, why?
King.
Is it what?
King.
It's king? Is that called king?
Like the shape is.
Oh, is it? Cusp. Okay. Even the cusp I don't like it, but at least it makes sense. Okay, yes. But where does this say that the value, the graph should not be a cusp, like you call it, cusp? Where on that equality we have, it shouldn't be cusp? Any of those who said no, can you elaborate on that? So you're saying, I'm assuming that you're saying the same thing, that, okay, at this point we have this cusp, and it's not continuous. But which part of this equality says the cusp is not continuous? The function is not continuous at cusp point. Actually, there's nothing saying that. Limit of the function as x approaches to 5. Look, I'm approaching to 5 from both sides, yes? They are getting to exact same point as the value of the function is. What is that value in this case? Okay, call it 3. But that limit is 3, and the same point gives me 3 as well. Sorry. It doesn't have being cusp there. It doesn't kill continuity. It kills something else. It kills, can anyone remember? Yes? It's not differentiable, something that we will study later this week and early next week. It is not differentiable, but it is continuous. So there is no problem with the continuity of that function. Are you happy with that? Okay. Cool. Any questions, any comments there? And keep in mind that this is type of work I want you to show. So this then implies that f is continuous at x equal to 5. Yeah? When you look at this limit here, one way of studying it is what we said. Well, the left limit exists, the right limit exists, and these are the same thing. But there's also another rephrasing of this into wording, which says that limit is given by substitution of the value into function. Or you remember that before we had in some cases that the value of the function is given by substitution, yes? Direct substitution, yes? Those are the functions that we already noticed. They are continuous. In other words, if I want to write this down, other way of saying this is that f is continuous at A if f is continuous at A if the limit as x approaches to A of f is given by direct substitution. That's another way of reading that formula. And we want that because we already talked about then as a result, corollary. corollary is that all polynomials, rational and irrational functions are continuous on their domain. Why? Because remember, limit of polynomial as x approaches to a is p at a. Direct substitution. We called it direct substitution, but other way of looking at or calling it is that every polynomial is continuous everywhere in their domain. For the rational functions, yes, you have the same thing. The only thing that you have to be careful is that q at a is not 0. That's already the values of a which are in the domain. Remember, domain of rational functions are the ones that are making everything but the ones that making denominator 0. Yes? And the irrational ones also goes the same way. You can direct substitute and get those ones. What else? I know that sine x, cosine x are continuous everywhere. Why? Just look at their graph. Every point you pick, when I'm approaching to those points, the values of the function gets closer to the value of the function at that point. Exponential functions. And logarithmic functions are continuous on their domain. So we already know lots of functions of that form. But I need to learn a bit more. How about the other operations? When we add two functions, when we multiply them, when we divide them, when we take root, when we find the power. So this is theorem, which is the corollary of limit laws, basically. So if f and g are continuous at a, then f plus g, f minus g, f times g, c times f, a constant times f, all these ones are continuous at a. Also, f over g is continuous at a. We have to be careful when we're doing the quotient thing. The denominator cannot be 0. If g at a is not 0. Or in other words, f over g is continuous in its domain, wherever it is continuous in its domain. F to the power n, I can add this one here, f to the power n is also continuous because of the limit laws. And the nth root of f is continuous at x equal to a. If we should be careful, if GA is positive when n is even. So we have a whole bunch of things that are continuous then. And if someone asks you, for example, find all the points at which this function is continuous, you just try to apply these rules and identify what points make the function discontinuous. So find points at which f is not continuous. So the first one is this function. Instead of writing not continuous, write where is continuous. Okay? And then I will use this other one. F of x is cosine x over 3 minus sine x. Go ahead, please, go ahead and complete this one. I'll give you 90 seconds. You focus on the first one, and writing is what matters. What is the question? Yes, please.
Do you know what COR stands for?
Sorry, what was it?
COR, all fault, non-linear rational.
Are you talking about this part?
Above. First line. COR. Bracket or.
Oh, corollary. Corollary. Result or outcome of something. Corollary. It is corollary of limit laws. So these are all limit laws. Oh, sorry. That one is direct substitution law. That's the result of that. Those are the corollary.
And then THM is theorem.
That's, I wrote as a theorem, but just straightforward result of limit laws. That's okay.
What is he saying?
So when it comes to this one, what you should write down, you can either reference one of these things here, or you can say that, okay, numerator x plus 1 and the denominator are polynomial, so continuous on the whole real line. Means that every point you give me, both numerator and denominator are continuous at, okay? But there is a fraction here, or quotient, and when it comes to the quotient, the rule over there we have to apply. So only f is not continuous at points that make denominator 0. So this means, f of x is continuous on all real numbers, but the ones that makes the denominator 0. We take away the things that makes denominator 0. That's the only way quotient of two polynomial can get discontinuity. But this is simple calculation. X squared minus 5x plus x means that x minus 3 times x minus 2 must be equal to 0. Yeah? Factoring. And there are only two values there. So f is continuous from negative infinity to 2, from 2 to 3, from 3 to positive infinity. That's all you have. X squared minus 5x plus x is equal to 0. I'm solving that. Only the denominator equal to 0. I'm only solving that one. Yes? And there are only two solutions for that. Huh? How about the second one? Numerator cosine x. It is continuous. Yes? Denominator 3 minus sine x, subtraction of two functions, continuous functions, it's continuous. So cosine x and 3 minus sine x are continuous everywhere. It means that it's continuous all the only problem that could come up here is that something can make denominator 0. In other words, f is continuous on all x's in R, but the ones that make the denominator 0. Is there any number that can make denominator 0 in this case? Can anyone say why? I can see some people saying no. Yes, please.
The range of the sine function is negative 1.
To be able to cancel 3 minus 3 equal to 0, sine x must be 3, but we know that sine doesn't go beyond 1 and negative 1. In other words, there is no such point in this function or in the real line that makes this equation hold or can solve that. There is no zeros there. So that means that the function is continuous on the whole real line. Any questions, any comments for me? When it comes to the functions that I have to evaluate the left limit and right limit, I can rewrite the definition in terms of left and right. Remember, the function is continuous at A if this is equal to A, yes? Now, if it happens that I have piecewise defined function, or my function, to evaluate my function, I need to consider left and right, this would mean that left limit must be equal to right limit. They both must exist, and they must be equal to each other. This is instead of writing that. And then this must be equal to the value of the function at A. These two things are the same thing. The second one, we are a little bit writing it finer, specifically when it comes, when the time comes dealing with piecewise defined functions, or the functions that we have to consider left limit or right limit. Does this make sense? Yes? Then, how about we run a poll today? I click your question. This is a function given, some parts of the formulas for the function has variables in it, a, b. And the question is that for what values of a and b, this function is continuous everywhere. What is the function? You can see it. I'll give you 2 minutes. You work on that. I'll write down the function on the board so that you can see it on the board as well. So you have to understand which points you're going to check, and for which point, what condition you get for A and B, and try to solve those ones. And by the way, you will need this limit when you're working with the last part. So I'll give you another 30 seconds, maybe. Okay, I'm closing the poll in 10 seconds. Four, three, two. Okay. First thing, the way the question is asking, the first thing you have to do is to make sure that you are identifying where these things are continuous. For example, I know that most of you will start from -1, checking -1 and 0, but the question, the way it talks about asks the result is that for what values of A and B, F is continuous on R. It's not asking only continuous at -1 and 0. So the way you should start is this, that no matter what is A or what is B, for x, 2x plus A, no matter what is A is going to be a constant if we can find it, yes? 2x plus A is a polynomial, and so it's continuous. Continuous everywhere, but when it comes to this function, it only takes care of values of x less than 1. So as a result of this, f is continuous for all x's less than -1. Yeah? How about x squared plus 3 over x minus 1? Is it continuous everywhere? Is it? No, where could be the problem? At 1 or, yes, at 1, yes? But is the 1 in this interval? So then, where this function is defined using this is okay. So I'll say x squared plus 3 over x minus 1 is continuous on everywhere but 1. As a result of that, f is continuous for all x's between -1 and 0. Why didn't I include 0 and -1 there? Why didn't I include 0 and -1? The function f is not given by this formula around -1 and around 0. So I have to separate -1, 0 and study them somewhere else. This is only one side of a story. This guy is the other side of a story. And they are, yes, they are continuous for between the boundaries. But at the boundaries, we have to consider both sides. There is third thing. B sine x over x is continuous on all real numbers but 0. But when it comes to the function, working with the function f, this thing gives values of the function for x is bigger than 0. So that means that f is continuous on everything bigger than 0. No matter what is b, that's just a constant, and that's good. This part you have to write when the question is asking specifically, where show that the function is continuous on the whole real line. Now, I have taken care of most of this domain, but 2 points. At 0 and at -1, I haven't yet started checking it. At x equal to 0, now I have to check 3 things. Limit of the function as x approaches to 0. Wait a minute, at 0, I can approach from this side or from that side. So I have to separate these 2 cases. So plus, it must be equal to limit of the function as x approaches to 0 from the left, and then the value of the function at 0. Now, when x approaches to 0 from the right, what is the formula I have to use? What is it? What is it? No, I don't hear anything. Yes. X is bigger than 0. The third one, yes? So I am going to use b times sine x over x as x approaches to 0 from the right. For this one, I have to check x squared plus 3 over x minus 1 as x approaches to 0 from the left. And for this one, well, I know what is f at 0. Well, x equal to 0 is here, so I have to use this formula. That gives me 0 squared plus 3 over 0 minus 1. Okay, now, what is, okay, b is constant, yes? So here you can use constant multiple. Constant multiple law. So if I know what is sine of x over x, I'll multiply it by b. What is limit of sine x over x as x approaches to 0? 1. Well, how? It needs some work, but you have to study, you have to watch that video. Here, it is one-sided limit of that. But if we know if it is, the limit exists, that one-sided limits are also equal to that. So this will be b times 1. Here, I'm using direct substitution or continuity of rational functions. This is 0 squared plus 3 over 0 minus 1. And that is two equalities. But when you put together, you see that b must be equal to negative 3. The condition that f must be continuous at 0 gives me these equalities, which turns out to be an equation for b. I solve it for b, and I get negative 3. How about x at negative 1? At x at negative 1. So limit of the function as this goes to the negative 1 from the left must be equal to the limit of the function as x goes to negative 1 from the right. And that must be equal to f at negative 1. So now I have to do one by one all these works. But these are direct substitution when we are working from the left-hand side of negative 1. This is the equation. So I have to have 2 times negative 1 plus a. Direct substitution would do this part. Limit negative 1 from the right, I will use this other one. So negative 1 squared plus 3, negative 1 minus 1. And f at negative 1 goes with the same formula. So what I get here is negative 2 plus a equals 4 divided by negative 2, which is negative 2. Result of that, a is 0. So a must be 0, b must be 1. We good? Yeah? Any questions, any comments? I have a small piece still left, so I need to use that at least 2 minutes of that. Yes, please. R but 0. But 0. You take away 0. Any other questions? Focus on writing. You have to do step by step everything.
That's weird.
We already covered limit laws. But what about the composition? So when f and g, when you want to compose them, so this is another theorem, says let limit of g as x approaches to a exist and equal to L. And f is continuous at L. So a function is continuous in the limit value of the other function. Then FOG has a limit as x approaches to a. The way this is calculated is interesting, that if f is continuous at the value of the limit can go inside the function and evaluate it. Result of this will tell you that if f and G are continuous, FOG is continuous. So corollary here is that if G is continuous and F is continuous on the range of G, then FOG is continuous everywhere on the domain of G. Or if F and G are continuous everywhere, you compose them, you will get a new continuous function. Okay? I think I will stop here. Have a great day, and see you all tomorrow. Thank you.
How come for here you don't include it?
As x negative 1,
Small numbers.
to look at both left and right. This function only considers one side of negative 1. So this function cannot say all this slowly and just equal to negative 1. That's why we have to consider